So previously we looked up on the power rule. Now we're going to see what happens if there are two different functions that are multiplied together. For example, if we have something like this, 2x squared plus 3x plus 5 multiplied by x to the power 5 plus 4. So one thing you could do is you could expand this and then apply the power rule, or let's try to find out another way where we can do the differentiation in a much more easier process, because there might be some instances where you can't multiply them easily. Let's say there would be some kind of power over here, and let's say there would be some kind of power like this, so it's going to be a difficult process for you to do that. So let's try to figure out a way that we can easily differentiate two functions that are multiplied together. Alright, so let's bring the definition of a derivative that we had learned previously. So the limit when h tends to 0 for a function f of x, this would be for a function of f of x plus h minus f of x divided by h. So this was the definition of a derivative. Now let's consider the function not to be just one discrete f of x value. Let's think of two different functions multiplied together. So we could say that there is some kind of function f of x multiplied with another function, let's say g of x. Alright, so we have these two functions that are multiplied together, and what you have to keep in mind is that this f of x and g of x are both in terms of x. So if this is true, we can now rearrange this derivative definition so that this satisfies our new expression f of x times g of x. So instead of writing f of x plus h, now I will be writing f of x plus h times g of x plus h. So this limit definition would turn out and be something like this. I will write limit as h tends to 0 for f of x plus h, and then times g of x plus h, and we had the f of x subtracted, but in this case it would be f of x times g of x subtracted. So it would be f of x times g of x, and then we have to divide this whole expression by h, right? So we did that. Now so far we didn't do anything extra, we just simply plugged in f of x times g of x into our expression. But now what we are going to do is we are going to try to rearrange this thing and try to express it in a different way. So let's try to write this whole expression in a different way. Now let's take the limit again. Limit as h approaches to 0 for the function f of, for the function f of x plus h times g of x plus h. But instead of subtracting f of x times g of x directly, what I will be doing is I will be adding and subtracting two extra things at the same time. And when I'm doing that, it won't make any difference because I'm adding it and subtracting it at the same time. So ultimately both the effects are going to be cancelled out. So what I will be doing is I will be keeping some space over here, and I'm going to write minus f of x times g of x. So this whole part I did, f of x times g of x minus f of x times g of x, this whole thing is exactly this whole thing. And then we have to divide by h, right? So we have to divide the whole expression by h. So far this first line and this second line are no different. But what we are going to do is, as you can see, I've kept some space here, so obviously I'm going to do something here. But what we are going to do is we are going to add a new term to this expression and also subtract that new term. And we're doing that so that it doesn't make any difference to our function, alright? Because we don't want to change the definition of a derivative. What we are doing is we are just manipulating the expression and doing some rearrangement in the function, just for the simplicity, just for figuring out a pattern, alright? So the term that I'm going to add and also subtract is, let's subtract the term first. So the term would be f of x plus h, and then I will multiply the g of x. So this new term that I just subtracted out of the blue will be basically disrupting the equation, because it's a new term that is added to this expression. So what we have to do is we also have to subtract this term so that it doesn't create any external effect in our function, in our equation. So let's just subtract that also. Let's just add that up also, so that the subtraction and addition gets cancelled out. So now I'm going to write f of x plus h, and then I'm going to multiply with g of x. So this expression plus f of x plus h times g of x, and this minus f of x plus h times g of x, these things are going to cancel out each other. So ultimately we are remained with this and this expression, which is the first equation we have written. So all these things are nothing but the definition of a derivative, but we're just seeing it in a different form. And the usefulness of this is that we can now take some f of x plus h and g of x common from both the expressions. So let's do that. As you can see from the first line over here, we can take f of x common from this expression, and then also we can take f of x plus h common from this expression. So let's just do that. So if I take f of x plus h common, it would be f of x plus h, and then I will be giving a bracket over here. Then I will write g of x plus h minus g of x, right? And also there's the second part to this function. So we are going to now take g of x common. So because we can see that in this part we have f of x plus h times g of x minus f of x times g of x. So we will be taking this g of x common. So let's do that. Let's take g of x common. So it would be plus g of x, and when I'm taking g of x common, what will happen is we can write this as f of x plus h minus f of x. So we can write this as f of x plus h minus f of x. And you have the h divided at the end, so let's just write that. So let's write the h that is divided, and also we have to put the limit that h is going towards 0. So now we have rearranged the original definition of the derivative and represent it in a different form. And the usefulness of this form is that we can see a pattern out of this. So now let's just do something. Let's just break this equation up. So we can simply write this as f of x plus h times g of. So I think we will need more space, so let's just create some space over here. Let me just erase this and create some new space. So what I want to do is I want to separate this this group of expressions into two parts. So I want to take this as one expression plus this as another expression, and that would help us in a different way. We're going to see that in a bit. So what I can do is I can write this as f of x plus h, and then we have the g of x plus h minus g of x by h multiplied, right? But what I will do is I will write it in this form. I will multiply this whole expression, would be written g of x plus h minus g of x, but the h will be divided onto this one, right? Because both of them are multiplied, so it doesn't matter in which denominator you place it, just place it somewhere. So we did it in this expression, so we put the h over here. So this h is over here, and then we will do the same thing with the right hand part, that is g of x times the f of x plus h minus f of x. So if we do that, it's going to be plus g of x times f of x plus h minus f of x, and then we're going to divide this by h. So we just broke the whole whole expression into two parts. And also remember that this whole thing over here has the limit as h approaches to 0. And the cool thing about limit is that we can distribute the limit into different functions separately. So we can take the limit, we can write this as limit as h tends to 0 for f of x plus h, and then multiplied with, again we are going to take the limit for the second expression separately. So we're going to write limit as h tends to 0 for g of x plus h minus g of x divided by h. And also we're going to do the same thing, but as you can see that g of x, this g of x doesn't have any h expression, so we don't need to take the limit, because the limit is basically tending to 0 for h, and g of x doesn't contain any h value, so we don't need to take any limit for that. So we can simply write g of x. All right, so we can simply write here g of x, and then we can see that this part f of x plus h minus f of x by h, this expression has a h with it, so we are going to be taking the limit for this expression. So we're going to write multiplied by limit when h tends to 0 for f of x plus h. Let's not give this bracket over here, let's just write it again. So f of x plus h minus f of x divided by h. Now look at this carefully. So we had simplified from the definition of a derivative and did some algebraic rearrangement, and we have finally reached in this line. And if you look carefully, you are going to see some pattern, and you're going to realize that you can simplify this further, because essentially the definition for a derivative was in this format. So if we want to differentiate f of x plus f of x, then the derivative would be given by this formula, right? Given by this limit. And if we see something in this pattern, for example f of x plus h minus f of x divided by h, it simply implies that this is the derivative of f of x. But instead of this, if something was in the form g of x plus h minus g of x divided by h, then it meant that this is the derivative of g of x. So using this concept, if we look carefully at the last line, we are going to realize that this expression over here doesn't have the derivative definition with it. It simply has f of x plus h, right? And the idea is that as h is 0, as h is tending towards 0, and if we plug this 0 directly into the formula, we aren't seeing any problem. So I could write this as f of x plus 0, which is f of x. So simply this whole part can be written as f of x, because if you plug in h equals to 0 in that expression, you are not getting an error. So the limit when h is tending to 0 would simply be f of x. And then if you look at the second part, the second part that is multiplied, this is simply the derivative of g of x, because look, it has the derivative definition with it, because it's saying that g of x plus h minus g of x divided by h, and we are also taking the limit when h is approaching to 0. So this is the derivative of g of x. So we can write this as times g prime of x, which implies that this expression is going to evaluate to the derivative of g of x, right? So now we're going to do the same process with the next term, all right? And if you see that the next term is basically g of x, so we will be simply writing plus g of x, and then you have limit as h tends to 0 for f of x plus h minus f of x divided by h. And this expression over here, it's simply the derivative of f of x. So now instead of writing all these things, what we can write is f prime of x. So this last part can be written as f prime of x. So this is the most simplified form we can we can ever reach with this product rule. So we have simply written the simplest form, and this is going to be the product rule formula. So for any two products, products of two functions, if we want to find the derivative of that, we can simply use this formula. So let's try to see what this formula is saying. So it's basically saying that if you have a function f of x and another function g of x multiplied with it, then if you want to differentiate this function, the final result would be f of x, which is the equation itself, multiplied with the derivative of g of x, so which is g prime of x, and plus you are gonna multiply the g of x function as is, all right? Then you're gonna times the derivative of f of x, so it's gonna be f of x times g prime of x plus g of x times f prime of x. And in some books or in some resources online, you can see, or even maybe at your school, you will see that this notation isn't used much, and you are most familiarized with UV notation. So sometimes people say that let this f of x be u and this g of x be v. All right, so sometimes people use u and v instead of writing f of x and g of x, and they try to write in this form, that is uv, if uv is a function, which means two functions multiplied together, and if you differentiate u and v, then the final result would be d dx of u times v plus d dx of v times u. So you can think of this in a much more simpler way. You can think that what I'm doing is, if I have two functions multiplied, firstly I would take any part of the function. Let's say if I'm considering f of x, then I would differentiate f of x and then simply multiply the other function directly with it. So if I have, let's start with an example. It's going to be much more simpler if you do that. And also, if you don't like to write d by dx over and over again, what you can do is you can simplify this and use u prime. So d dx of u means derivative of u, and to show this, you can also write u prime. So d dx of u and u prime can be used interchangeably. So